Hello, everyone. I'm sorry that it took me a little while to get started here. I keep getting bumped out of the system, and it looks like other people are having problems too, since there's not very many of us in the room right now. But I'm going to get started, and if something happens and I get dropped off, I'll just log back in as soon as I can. And hopefully you all will do the same if that happens to you. Can you all hear me okay? Okay. All right, well, this week we're going to be talking about system protection. But before we do that, I'm going to talk about the homework that you had last week. And in that homework, we were talking about blocking and non-blocking I/O. And you're supposed to give 3 examples or 3 situations in which blocking I/O should be used, 3 in which non-blocking I/O should be used, and then answer the question about why not just implement non-blocking I/O and have processes busy wait until a device is ready. So the answers to this question are going to vary quite a bit. There's a lot of different things that are blocking I/O versus non-blocking. But here was the answer that I came up with. Blocking I/O is used when a program needs to wait for the I/O to occur before it can continue. Some examples would be an application program waiting for data to be read from disk, waiting for input from the keyboard. In other words, the application has to get information from the user before it can continue, or waiting for information to be read from a CD-ROM. Okay, you could have come up with lots of different examples, and I'll read through each of those. You're not going to match my examples exactly. Non-blocking I/O, on the other hand, is often used when the input can be coming from multiple sources, or it may not be available. In other words, things like waiting for input from a mouse or a keyboard, that might not be available, but the application, if it's not something critical to the application could continue. So for example, reading from a keyboard could be blocking or non-blocking, just depending on the way it's set up. Non-blocking I/O can also be used when the application doesn't need to wait when writing to a device. Some examples would be a GUI interface that reads from the mouse and keyboard, a web server that's waiting for requests to come in, or writing to a printer would be an example of non-blocking I/O because the application won't necessarily wait for the printing to happen before it can continue. So again, you can have a lot of different examples of what blocking and non-blocking I/O would be. And I'll examine those to make sure you understood the concept. The reason we don't use non-blocking I/O all the time is that it's more complex. Rather than the application just sitting there and waiting for the I/O to occur and then continuing when it's done, the application can go about its work, and somehow it has to know when the I/O happened. So a lot of times this is implemented as an interrupt-driven kind of capability, where you would have maybe multiple threads, not necessarily in your program, but in the system itself, where one thread will be waiting on the I/O while the application is continuing. But somehow, when the input comes in, the application has to know about it. So you can do something where you poll, where you're actually looking over and over and over again, a busy wait to see if the I/O occurred. But this actually is inefficient when you do a busy wait. So the second part of the question here, I say writing code for non-blocking I/O is more complex because there needs to be a way for the application to know when the I/O occurs. And while you can use a busy wait, it is less efficient than interrupt-driven I/O. Okay, any questions on that? Okay, Well, let's continue then on to our topic for this week, which is protection. This week we'll be talking about the goals and principles of protection in a modern computer system, explain how protection domains combined with an access matrix are used to specify the resources that a process may access, and examine capability and language-based protection systems. So some of the goals of protection are to increase the reliability of a system that uses shared resources. We want to make sure that an application, whether intentionally or unintentionally, is not corrupting the resources that another application needs. We want to be able to prevent intentional violation of an access restriction. Okay, we want to make sure that our programs and our users are not accessing things they're not supposed to be. We want to ensure that active components use resources according to policies. In other words, programs, processes, they're only using the resources the way they're supposed to be using them. We want to be able to detect latent errors at the interfaces between components. In other words, we want to make sure that there's nothing that we're doing where one process or one component of the system is inadvertently affecting another component or process in the system. And we also want to be able to tell when something is an authorized use or an unauthorized use. In other words, whether a user or a program is allowed to access a resource or not. And so we want to be able to do these things in order to protect our system. One of the important principles is called the principle of least privilege. The principle of least privilege says that programs, users, and systems should be given just enough privileges to perform their task. And what this basically means is that we want to make sure that any program or any user only can access, only can modify, only can read from resources that it needs to. Okay? And what this does is it ensures that a compromised component does minimal damage. In other words, if the system is set up so that I do not have admin authority on the system, that means I can't go in and install things on a system because I don't have those privileges. What it means, though, is anything I do have privileges to, of course, I can destroy, I can do whatever I want to them if I have the right authority. But if I only have authority to my programs, to my files, then the only person I can hurt, basically, is myself. Okay, and that's true of all the components, not just users, but anything in the system. If we limit what each component can access, we're actually limiting how much damage a component can do, whether it's intentional damage or unintentional damage. Applications can be written with fine-grained access controls. In other words, we may be able to say, well, this can only access this file, or even more specifically, it can only access this file for reading. You can't write to a file, and that type of thing. So rather than saying you have access to everything, we can narrow the access and actually make it very, very narrow so that an application can only access those very specific things that it needs to do the work it's supposed to do. We can further restrict access by enabling and disabling the privileges. In other words, rather than having an application be able to access a file all the time, why not make it only have the privileges to access that file when it needs to, and when it's done using the file, take away that access. And then that will, again, help to protect the system. Another thing that's important when you're talking about privilege is to have audit trails, to have log files that are used to trace all the protection and the security activities that happen in a system. Okay, so then you can kind of look at a log and see, wait a minute, this process was not supposed to be able to access something. It didn't need to, and you can go and correct the situation. Okay, so the principle of least privilege says that you only have access to the things you need in order to do the work you need to do. And I'm guessing most of us are guilty of not following this principle. And I'm not just talking about in my program. My system that I work on right now is a Windows system, and I've given myself administrator privileges, okay, so that I can install whatever software I want and everything else on my system. I have full access to everything. What that means, though, is that my system actually isn't very secure, because most of the time I don't need that much authority. So I'm leaving myself more open to malicious attacks, as well as just messing myself up accidentally. Okay? To make my system more secure, I should probably only give myself user authority and then only take on administration authority when I absolutely need it. Okay, so think about that even on your own system. Do you have administration authority on your system? And if you do, you're not really following the secure principle of least privilege. Because if you don't need to be actually accessing system files and so forth on your system, why give yourself that access? Why only give yourself that access? Why not only give yourself that access when you absolutely need it? Does that make sense? Okay, as we talk about protection on a system, we'll be talking about the domain of protection. And there's certain terminology that we use when we talk about this. We say that a computer system is a collection of objects. And here we're not talking objects the way you may think of as in Java, although it can mean that. But here we're talking a more general definition of objects, where we have things like hardware objects and software objects. So a hardware object could be something like a CPU, for example, might be a hardware object because it's a physical thing in your system. A printer, a disk drive, all those are hardware objects in your system. You might also call them components. But when we're talking about domains of protection, when we talk about an object, we can be talking about hardware. We can also be talking about software objects. And software objects would be things like files and programs. Okay, these would be, software objects in the system, not something physical, but something, we do as we manipulate the bits on our system. So when we talk about an object, when we're talking about protection, we're talking about both hardware and software. Each object has a unique name and can only be accessed through a well-defined interface. And processes should only be given access to the objects that it needs and has the authority to access. Okay, so the resources are the objects in this domain of protection. And again, we're talking a little bit about a need-to-know principle. Okay, this is kind of like least privilege, but when we're talking about access to data or information, you may have heard people use the term need-to-know. In other words, you only let people access the information that they absolutely need to know to do their job. Okay, and so we kind of want to have this kind of domain of protection where only processes that actually need the resource, need to know the information on that resource or whatever, they are the ones that are given access to it. So when we look at the domains, we have what's called a domain structure, okay? And what we're actually looking at is how a process within a process domain can access certain resources. So a process operates within a protection domain, and a protection domain is a collection of access rights. Access rights are the ability to execute a certain operation on an object. And so for each object in a domain, you can say, what is the right set for this domain? So here's an example. Here in domain 1, you would have access, both read and write access, to object 1 and to object 3. You would only have execute access to object 2. So you couldn't read or write. So a lot of times, if someone doesn't have administrator access, for example, on a system, they will be able to use an application. They have execute rights to that application, but they may not be able to overwrite it or copy it or that type of thing. Okay, so that would be an example of some rights in a domain. Over here, we have two different domains, and there's some overlap between them. In domain 2, we can write to object 2 and print to object 4. And in domain 3, we can execute object 1, read object 3, and print to object 4. So you can think of here, we might have something like a shared printer where these two different domains share that printer, and they can both use that printer. Okay? So that's kind of one way of looking at a domain structure. What are the rights that in that domain that are granted for a particular object? We also want to look at whether the protections are static or dynamic. With the static protection domains, the association between the process and the domain is fixed. In other words, a process belongs in a certain domain, and this doesn't change throughout the life of the process. So if it's in domain 1 when it starts, it's always in domain 1. We may need to do something like change the content of the domain in order to adhere to the need-to-know principle. In other words, we may need to change those accesses within the domain as the process executes. But for the most part, the process is going to stay in the same domain, and we can only change what it can do by actually changing the domain itself. It can't switch between domains. If it can switch between domains, that's called dynamic protection. And here, the association between the process and the domain can change. Domain switching will allow a process to switch from one domain to another. Okay, and so your book goes through some examples of operating systems and how their domains are set up. It talks about Unix, and it also talks about Multics. But basically, all we're really looking at is what objects can a process access or a user access or whatever within a certain domain, and does that process always stay associated with the same domain, or can it switch to other domains in order to get other access rights to objects? Any questions on what we're talking about in general with domains? Okay, just to be clear, we're talking about domains, and you might be thinking, well, what is a domain? What exactly does that mean? And a user can actually be a domain. So what domain a user is associated with will affect what set of objects that user can access. So the set of objects that can be accessed depends on the identity of the user. So when we do domain switching, the domain is switched when one user logs out and another one logs in. Or if I log out as a user on my system, and then I log back in as an administrator, my domain will change. I will have switched my domain from one set of objects that I can access to another. A process can also be a domain. And then here, the objects that can be accessed depends on the identity of the process. And here, to switch domains, the process can't change its identity, but what it can do is send a message to another process to do something for it. Okay, and remember way back in like the first week, we talked about message sending and that type of thing. And so here, we're talking about a domain being switched. What the process is actually doing depends on which process is executing at the time. So I could have process 1, and it may only have access to objects A, B, and C, and then it needs to access object D, but it doesn't have access to it. It can send a message to another process, and that process will begin executing and accessing object D. And that's a domain switch. It switched from the domain that my first process had to the domain that the second process had. And then finally, a procedure can be a domain. And by a procedure, you could think of this, if you're familiar with Java, if that's the language that you know, you can think of a procedure as being a method in Java. And if you think about methods in Java, you've probably talked about global variables and local variables and scoping your variables. With a procedure or a method, the objects that can be accessed are the local variables defined in the method. Okay? So when we're talking about procedures, the set of objects that can be accessed is the set of local variables defined in the procedure. The domain is switched when another procedure is called. Okay, when you call another method, it has its own local variables that it can access. Or if you make a call to a method in another class, that class has access to different variables, different resources that it's using. Okay, any questions on that? Okay. So let's take a look at an access matrix. And you know, we've been talking about domains and objects and what can be accessed. And one way to abstract it out, one way to kind of look at this, you know, not how it's actually implemented, but how you can think about it, the abstraction that you can think about with it is by looking at it like a matrix. Here we have different domains, 1, 2, 3, and 4. And then we have different objects that can be accessed in the different domains. And so here we're looking at the different domains that may be in a system and the different resources or objects that may be in a system. And we can see here for file 1, it can be read in domain 1 and read and written in domain 4. File 2, domain 1, domain 2, and domain 4 cannot do anything with file 2, but it can be read in domain 3, and so forth. So here we're just looking at the different rows that represent the domains. So for instance, domain 4 has read and write access to file 1 and read and write access to file 3. Or we can look at it as the objects, which are the columns here. And I don't have a pointer that points down, but we have the different columns, and we can look at what domains can access that particular object. So the columns are the objects, the rows are the domain. So when we say access I and J, that says if I have a process in a certain domain, what objects can it access? In other words, what different operations can it do on the different objects in the system? So in domain 1, for example, if I'm looking at file 1, it can access that file only by doing a read. Okay, and so that's kind of how you look at this access matrix. Now it can get a little more complicated because we may want to specify policies in a matrix. So we already know that something in a domain can only do the operations that are specified in the different columns for that domain. So in here we can access file 1 and file 3 only by doing reads if we're in domain 1, but we can expand this to say it can also do a switch to another domain. Okay, so we've expanded it to not just be the objects, but to make the domains themselves be other objects in the system that a domain can access. Okay, so a user who creates an object defines what can be done with that object in what domains. In this case, file 1 can be read in domain 1 and read and written to in domain 4. And whoever created that file would specify that. But we can also say when a domain is created, what other domains can switch to that domain. Okay, so we're getting a little more complicated because not only do domains specify what access it has to objects, but it also specifies how can we switch to domains if we're allowing domain switching in our system. Okay, so switch is a type of policy where if it has access rights, if a process has access rights and those access rights include switch, it can switch from one to another. So a process in domain 4, for example, can switch to domain 1, and a process in domain 2 can switch to domains 3 and 4, and a process in domain 1 can switch to domain 2, but a process in domain 1 cannot switch to domain 4 because it doesn't have that access. Okay, so again, this is just a generalization of kind of what are you going to allow? What are the policies you're going to have in this system? Okay, we can also look at whether a domain can copy rights from one domain to another. And so an asterisk here in our matrix says that an access right can be copied from one domain to another. And so domain 1 has write access to file 3, but the asterisk here means that it also can copy that right from one domain to another. Okay, so what we're saying is that a right can be copied from one domain to another. Here we have also like domain 2 here can copy the read operation from one domain to another. Okay, so it can copy that access. So again, this would be set up when the objects were created, and again, we're saying, okay, what are the access rights? So in addition to having the read, write, and execute kind of access rights, we also say which of these rights can be copied within the column for which that right is defined. So in other words, if domain 1 can copy write access, it can copy that to one of the other domains in that column. You can also limit how the copy can be done. And when you limit how a copy can be done, this just says that you can transfer rights by saying, okay, you copy it from one domain to another, but then you delete it from the other domain. Okay, so we might be here. Here we did just a straight copy to copy from domain 2 to domain 3. But if when we copied from domain 2 to domain 3, the read access for file 2, if we also then deleted it from domain 2, that would be a transfer. We're actually moving the rights from one domain to another. And then the other thing is limiting the rights. In other words, here when we copied the read, which had the copy right added to it, when we copied the read from domain 2 to domain 3, we did not copy the right to copy it again. So domain 3 would not be able to copy the read access to file 2 to any other domain. Okay, so this whole matrix is kind of a shorthand to say what are all the things that can be done with these different domains and files, or objects, I should say. They're not necessarily always files in the system. Okay, another type of consideration that you have when we're talking about access rights is who is allowed to add or remove rights for an object. Okay, and the way that you can add or remove rights to an object is by having owner rights to an object. So the owner rights, saying this domain owns this object, whether it be a file or a printer or anything else, if an object owns that, then if a domain owns that object, then that domain is the only one that can add or remove rights for an object. So here you can see that domain 1 has owner rights to file 1. So domain 3, I misread that. Domain 3 has execute rights to a file. Domain 1, since it's the owner, can say, I'm going to remove the execute rights from domain 3, and then we would have a domain access matrix that looks like this. Okay, the same thing here is domain 2 is the owner of the rights to file 2. It can give itself write access because it's the owner. It can add that. We're not talking about a copy here. We're talking about an add. It can add the right to write to a file, and it can add it to another domain, the right to write to a file. So here we can see that domain 2 was the owner, and it added its own write access and gave itself copy privileges as well, and it also added write access to domain 3. So again, we're just specifying what the different domains are able to do with the different objects in the system. Okay, now what about changing a domain right? Okay, the control right allows a process to add or remove any right for a domain. Okay, so in this case, we say that domain 2 has control access to domain 4. So in this case, domain 2 would have the authority, let's say, to control domain 4. Okay, so any process executing in domain 2 could modify domain 4, and that's what this grid is showing us. Okay, so all it's really doing, an access matrix is really trying to simplify what can be done, kind of giving you a picture or a snapshot of what processes can do what to which resources in a system. And it depends on what domain that process is in. Any questions on what an access matrix is? Okay, then let's continue with now an access matrix is kind of something a human can see and say, okay, I understand now, as a programmer, if I'm going to implement an access matrix, I understand who can do what. And so now I need to be able to implement that table somehow, that matrix somehow in a program. And so there are a number of ways in an operating system that an access matrix can be implemented. The simplest one is a global table, where there's a table that looks kind of like this. It has the domain, it has the object, and then it has the set of rights that a process has to that object in that particular domain. Okay? So we're saying here's a domain, here's an object. It's actually a table in memory where it would have kind of 3 columns in the table, and it would have the domain, the object, and the rights. And we would index it, let's say, by the domain, look for the domain. When we find the domain, it says, okay, what objects have what rights? What are the rights to those objects in this particular domain? So this is actually very simple to implement. But the problem is the table will be very large because we have to do it for every domain and every object and all the rights for that object. So what happens is that the table, when it gets too large, it can't be kept in main memory, so we're going to have to be doing I/O. And as you recall, we want to kind of keep I/O to a minimum in an operating system because it's expensive. It takes time. So that's one of the disadvantages if you try using a table that's actually for every object and every domain in your entire system. The other thing is we can't group objects or domains. Okay, we have to have this entry for every single domain in the system. And there's no easy way to say, oh, show me all the domains that have read access to this particular object. Okay, we'd actually have to do a lot of searching through the table in order to find that information. Another way we can implement an access matrix is by using an access list. So in this case, each column in the access matrix can be implemented as an access list for that particular object. So each column is an access list, has an access list, and the access list is just ordered pairs, the domain and the right set in that domain. So now we can say, okay, for this object, what are all the domains that can access this object, and what are the rights that they have in this, the processes have in these domains? And it's very simple. We can just look at the access list for that one object and know the answer to that question. It also allows us to easily extend the access matrix to include a default set of operations. In other words, we might say if a domain's not listed in the access list, then by default it has these rights to this object. Okay? So that's just another way that we can implement an access matrix. And again, we're just looking at how to implement protection in an operating system. Another thing we can do is have what's called a capability list. So now, instead of associating the columns of the access matrix with the objects as access lists, we can associate each row with its domain. So each domain has a list of objects along with the operations that are allowed on that object. And that's called a capability. Capability is the object represented by its name or address, and the domain has a capability list associated with it. And so a process executing in that domain will be able to see, okay, here are the objects it can access along with how it can access those objects. So it's just kind of slicing that access matrix in a different direction, saying now we're going to look at, for each domain, what are the objects along with the allowable operations. And so to execute an operation on an object, a process would say, I want to do this operation. This is the object I want to do the operation on. And that object has to be in the capability list along with that being an allowable operation in that domain. Okay? So we can implement it basically two different ways. We could identify each object in the system by a tag, and the tags won't be accessible by a program. I kind of have a typo here, so this, I'll fix it before I send you these slides. But basically, each object will have a tag to indicate whether it's accessible or not. In other words, if the domain has that capability or not. Okay, so there'll be a tag to denote whether it's a capability or if it's accessible data in this particular domain. The tags themselves are not directly accessed by a program. Okay, so the tag can't be accessed. What the program does is it says, I want to be able to access this object, kind of, do I have this capability? And so you can look up the object, and the operating system can look up the object and see whether or not it has that accessibility in this domain. The other thing that you can do to implement a capability list is something we talked about back when we talked about memory and segmenting memory. You can have the address space associated with a program split into two parts. One is the stuff that the programs can normally access, the program's data and the instructions. The other part would be the capability list that the operating system would then access to see whether or not a process has access to a certain operation on a certain object. Okay, so there's lots of different ways you can implement this. Your book goes into a couple of different examples of capability based systems. The next way that you can access it, though, is using a lock and key. And to me, I kind of like this one because it makes the most sense to me. A lock and key implementation is kind of a compromise between access lists and capabilities. And the way a lock and key system is set up is each object has a list of unique bit patterns called the locks. Each domain has bit patterns called the keys. A process in a domain can only access an object if the domain has the key and it matches the lock for that object. And the list of keys is actually managed by the operating system. Okay, so this is kind of a nice way of using a bit pattern as a lock and a key, and if they match up, it means that process can access that object in that domain. Okay, so we have all these different ways that we can implement an access matrix, and there's a lot of trade-offs. If you're designing an operating system, which one do you want to use? Well, we already said that a global table is a simple way of doing it, but it can be large. So we have the problem that we wouldn't be able to have everything in memory, and we have to do I/O in order to search this table, and so it's going to be inefficient. Okay, so a global table may not be the best idea. An access list is good because it corresponds to the needs of the users. In other words, the access list, when you create an object, remember, we create the operations that are allowed on this object in the different domains. So for any object, you can kind of say, okay, well, here are the rights that we have to that object. But finding out what rights are in a domain is hard. Okay, remember, we're looking with an access list, we're kind of looking at the columns and saying, okay, what domains can access this object. But then to ask the other question, it's a little more difficult. If I say, okay, I have a domain, what are the rights for this domain? I'd have to search through all the different access lists in the system to see where that domain showed up. Okay, another disadvantage of an access list is that every access to an object has to be checked. So if the access lists are long, in other words, we have a lot of domains that can access, whenever anything is accessing that object, we have to go through that access list and say, is this a domain that can access the object? Oh, that's not it. Let me look at the next one, and the next one, and the next one, and then go through the whole list every time to find if that object can be accessed in that particular domain. A capability, on the other hand, since we're kind of slicing the application matrix in the other direction, a capability list is useful for localizing information for a process. In other words, here we're saying, okay, in this domain, what are the different objects I can access? So looking at it from a domain is more efficient. But what happens is if we want to revoke access across domains or revoke all the access to a particular object, like sometimes your objects get quarantined or something like that, and you want to say, okay, this object no longer has any accesses, you have to go through all the domains and revoke the access to that object in all of the domains. Okay, so that's a disadvantage there. Lock and key, this is both effective and flexible because the keys can be passed from one domain to another, and it's very easy to revoke it. You just take away the key. Okay, so lock and key from an implementation point of view, it's very effective and flexible. Most systems, however, use a combination of access lists and capabilities. Okay, so they kind of use a combination of the two, and lock and key is kind of a newer way or a less frequently used way of implementing an access matrix. Okay, now we also talk about access control. Okay, Hannon, I see your message that Hall is having a connection problem. If you're messaging with her, you can just tell her that she can. I will mark her present if she views the recording after the session is over. Eventually, she'll be able to get into Blackboard. So if you ever can't get into Blackboard during a session, just email me and I'll give you credit for being here as long as you watch the recording. Okay? And I'll send her a message as well. I'll send her an email. To continue about access control, we talked about how file systems control access to a file, where you can have a user and the user has certain privileges, and the privileges can access a certain file in the system. Okay, and we talked about that a week or two ago. Well, we can take that same idea and apply it to non-file resources, other resources in the system. And Solaris actually does this in their role-based access control. And it's a way of implementing the least privilege principle. So a privilege can be assigned to a process, and it's the right to execute a system call or use an option within the system call. Users are given roles, giving them access to privileges and programs. And so here we have a user which has a certain role. That role gives them privileges, and those privileges give it access to a certain process. So it's kind of a way of, implementing an access matrix using roles and privileges, similar to what we looked at with file systems. The other thing we need to be aware of is that we need to be able to revoke rights to an object. So we need options to remove the access rights of a domain to an object. And we need to decide whether it's going to happen immediately or will it be delayed. Can we do it, for one domain at a time, or does it have to be all or nothing? Is it general or selective? Can it be partial or total? In other words, do we have to revoke all the rights to an object, or can we just revoke, say, the read access or the execute access to an object? And then again, is it temporary or permanent? In other words, once something loses access rights, can they get those rights back again, or are they, done for good? They can never access that object again in the system. Okay, we're getting close to the end of our session. I'm going to keep recording. If you need to leave, feel free to do so. I totally understand, and you can just access the recording when it becomes available. Okay, so I know we only have a couple more minutes here, and there's a few more things I want to talk about. If we look at an access list, for example, and we want to delete access rights from the access list, it's pretty simple. We can search through the access list and remove the entry. This would be immediate. It's gone once we remove it. We can make it general or selective. We can go through and remove all the rights or just some of them for the different domains. It can be total or partial, and it can be permanent or temporary. So actually, when we use an access list here, we can see it's pretty flexible to delete a certain access right from an access list. If we look at a capability list, on the other hand, with a capability list, we would have to locate the capability in the system before we can revoke access to it. Okay, and remember, the capability is associated with the object in that domain. And so there's a number of ways that we can do that. One way is to just always revoke privileges, okay, on a periodic basis, kind of when a timer goes off, let's say, we're going to revoke all the access and then give processes the ability to reacquire the access. Okay, so this is kind of a way of saying, once you have access, I'm not going to let you have access to an object all the time. I'm going to periodically get rid of, delete the access for that object. But if you ask for it again, if you're still supposed to be allowed to access it, I'll give you the access back, the access rights back. So that's one way that we can revoke access to an object. We can also use back pointers. Okay, remember that the way capabilities work is they're based on domain. And what we can do is we can have a set of pointers that go from each object back to those domains, so that the object, in addition to the capability being known from a domain standpoint, the object will also know which domains have access to it and can revoke the rights to the object that way. Another way is through indirection. Here we can use a global entry table, which we talked about before, where the capability will point to the global table and the entry points to the object. And when we want to delete access to an object, we simply delete the entry in the global table. But that means every domain can no longer access that particular, has access rights to that particular object. And then finally, we can look at using keys. And again, a unique bit pattern is associated with the capability, and this is kind of combining what we talked about with capability lists and keys in locks, where we have a unique bit pattern with each capability. When the capability is created, it gets the key, the domain gets the key. The master key is associated with the object. We match the key for access, and to revoke that access, we just get rid of the master key, and then any domain that had a key that it was trying to match to that object, it would no longer match. Okay, so those are some different ways that we can revoke access to an object. Any questions on that? Okay, let's continue then to language-based protection. All the protection we've been talking about so far has to do with the operating system, and usually protection is provided by the kernel in the operating system. Yes, you can leave anytime you need to. You don't have to wait for my permission. Please feel free to leave. I know we're over time, and I apologize for that, but I want to continue going through the materials. So you can access the recording later. Okay? Protections usually provided by the kernel, and the kernel inspects and validates each attempt to access a protected resource. But we can also have protection in a programming language, which kind of allows us as a programmer to specify the policies for the allocation and the use of a resource. The language itself can provide software for protection enforcement, and this is helpful when you don't have hardware-supported checking on your system. And then also, protection specifications generate calls to protection provided by the hardware and the OS. So again, you can have additional protection in your language itself when you're writing programs by actually doing system calls that call the protection facilities provided by the hardware and the operating system. Compilers then will often enforce protection, and again, you know, we're talking here at a level that you can control as a programmer. A programmer can specify the protection needed for different resources at the time resources are declared. And you may have talked about this some in your Java course. For instance, in Java, you might have variables that are protected, private, or public. And other classes may or may not be able to access those variables, those resources, those methods even, if they don't have the right privileges. Okay, so with compiler-based enforcement, when you think about it in Java, you actually specify whether a method or a variable is private, protected, or public. And then the compiler will flag things if you try to access that resource and you don't have the correct privilege to access that resource. So protection needs are declared instead of being a bunch of procedure calls. The compiler can enforce that only things that are allowed to access private variables, for example, can access those. And then the protection is stated independently of the support provided by the operating system. In other words, if I have a private variable in Java, it's private whether I'm on a Solaris system, whether I'm on a Unix system, whether I'm on a Linux system, whether I'm on a Windows system. No matter what, the protection works the same because it's enforced by the compiler, not by the operating system. Okay? You don't have to do anything about it. You just declare things protected or not, or private or not, and the compiler takes care of providing the enforcement of that. And that's why you get compiler errors sometimes. It's enforcing, the compiler's enforcing the protection that you said was on an object or that another programmer said was on an object. And it's very natural for us to declare things public, private. We're used to doing that because we have data types, and when we declare, the return type from a method, we also declare its protection, whether it's protected, public, or private. Same thing when we're declaring a variable. We declare the type of the variable, but we also declare whether it's public, private, or protected. So we're kind of used to doing this as developers. So we can look a little bit at, what are the advantages or the disadvantages of kernel-based enforcement versus compiler-based. And when you look at security provided by the kernel is better than that provided by a compiler, because security for the compiler is only as good as the compiler itself. And if you think about it, we're downloading these compilers all over the place, and sometimes they're not as well tested, as secure, say, as an operating system. Not to say that all operating systems are secure, but you have a little more risk, I think, with compiler-based enforcement because the compiler itself has to do the enforcement. The other thing is you have to look at, with a compiler-based enforcement, if that's all you had, what would happen if somebody hacked into some code and changed something? They didn't hack into the source code, they actually hacked into the object code and made some changes. What's going to protect you then if you had no kernel-based protection? The kernel can also do a better job of protecting itself from modification. Okay, compilers, it's a little easier to modify a compiler either intentionally or unintentionally, but the kernel can protect itself a little better and also can protect access to specific files, because remember, the kernel kind of has access to everything, and if the kernel is your gatekeeper, it's a little more secure. Usually we use both kernel protection and compiler protection. When we have hardware support to memory access, the protection is even stronger. Okay, so if we can actually protect who's accessing or what memory, and that's actually enforced by the hardware, which we talked about way back when we talked about memory access, then the strength of your security is even better. So if you had to choose between kernel versus compiler-based, in terms of security, kernel offers better support. But again, often we have both. As far as flexibility, kernel-based protection is not as flexible, okay, because again, you can't change it easily. Here with compiler-based protection or compiler-based enforcement, there can be support that a programmer can use. In other words, we're actually saying this variable is protected or private or public. You wouldn't get that fine-grained protection if you were just using kernel support for enforcement. both a disadvantage and an advantage to a compiler is that a compiler can be changed and updated when necessary, so you can change the protection services offered by a compiler, and you could also change how the protection services are implemented in the compiler much more easily than an operating system. In other words, it's a lot easier, you know, if there was a security flaw in the Java compiler, for example, it's a lot easier to download a new Java compiler than it is to download and install a new operating system. And so that just makes it more flexible. A compiler-based enforcement is more flexible than kernel-based. And as far as efficiency, actually the most efficient is one based on the hardware. And so since the kernel is closer to the hardware-based efficiency is more, or hardware-based protection is more efficient, but realize that a compiler can be efficient when you're talking about checks being made at compile time rather than runtime. Checking things in the hardware happens at runtime in an application, but checking things like checking to see that you have the right access for a private variable, for example, can happen actually in compile time, so it's not happening when the code is actually executing. So that's more efficient in that case at execution time. Okay, to talk about Java in particular, Java has a lot of protections because Java was designed to run in a distributed environment where code could be run from both trusted and untrusted sources. Java applets can come from anywhere and you're executing that applet. Okay, Java code, Java bytecode can be moved from one operating system to another, and it can be trusted or non-trusted, and the JVM has to kind of have the protection to make sure that if it's coming from an untrusted source, it's not doing things it shouldn't. So the JVM in Java actually has many built-in protections, including a protection mechanism that's implemented at the class level. Each class is placed in a separate protection domain when it is loaded, and this protection domain depends on whether the source URL is trusted or not. It depends on what the digital signatures are on that class file, and it also depends on a configurable policy file as to what permissions are granted. Okay, so whenever you load a class, the class loader is looking at all these things. Where did this class come from? Is the URL for that class trusted or not? What kind of digital signatures are on that class? And what policies are there for things that are coming from different sources. Okay, and sometimes you run into problems. In fact, I run into problems with Blackboard where the version of Java I'm using doesn't match with the version for Blackboard, and so I actually had to go to a different level, or I have to say, don't worry if the signatures don't match, or don't worry, I'll take on that risk and let me run this application, because the Java virtual machine is actually trying to protect me from something it thinks I shouldn't want to access on my system. One of the ways that Java does some of the protection is through stack inspection. With stack inspection, when you're trying to access a resource in Java, it requires that the method assumes responsibility for the restricted access and that the method will do whatever it needs to ensure that the request is safe. Every method in Java, every thread in Java has a stack of ongoing method calls. In other words, you know, if we're calling something in one thread and that invokes something in another thread and that invokes something in a third thread, because we have all these threads going on since Java is naturally a threaded language. Each thread has its stack of method calls, and when a caller may not be trusted, the method actually executes the request in a do privileged block. It's a special block in Java which annotates the stack frame for the calling method. In other words, it says, okay, I'm going to do something that's privileged. Let me do it in this privileged block, and if the system grants it access, it's going to note that this had privileged access in this do privileged block. Anytime it tries to access that protected resource again, it'll use a check permission to see if the method has the privilege to access that protected resource. And if it finds that it has the privilege, it'll let it access that particular resource. If it doesn't have access, access will be denied. But if it hasn't been explicitly said, oh, it can't access it, then it really depends on how the operating system or how the JVM is implemented to say whether or not it will be given access at that time. I know this is a little confusing, but if you look at this picture, it makes it a little bit clearer. Let's say we have an applet, and that applet came from who knows where. It's not trusted. It doesn't have any permissions to access sockets on our local machine. But inside a class, it may have a get URL to open a certain address in the system. Now, when it does the get URL, the URL loader will then be put on the stack, and it actually does the get URL method. And in the get URL method, it does a do privilege block. And inside that block, it's opening a socket. Okay, so we can see it's opening something on proxylucent.com, and it's opening port 80. Okay, and so it has permission. If we look at its permissions, it has permission to do that. It has permissions to connect to lucent.com. Okay, so then, it does certain requests and everything's good. Okay, when it does the open, it actually, goes to the networking software. It can do anything with sockets. So it can open a specific socket and check to make sure that it can make a connection. So it's doing that checking when it does the open. Okay, so down at this level, it's checking up the stack to say, okay, whoever's doing this open, do they have the permission to do this? Okay, so the open checks to see that the URL loader that called it has the permissions to connect to that socket. Now look what happens here, though, when the applet then tries to do an open on its own. Instead of going through the URL loader, which has the permissions, it calls the open directly. Now it says, check to see whether anything in the stack has permission. We went directly from the untrusted applet to the networking code. There's nothing here that has permission to that socket. So here, this request would fail. So if I call it through get URL, if the open is called through the get URL, where the URL loader gets permission to access the socket, that works. But if my code tries to access a port directly, that doesn't work. Okay, so the get here would work even though it's opening an address, but it's the URL loader that has permission, but doing an open on its own will fail. And that's how stack inspection works. When I do this direct call, for example, this piece is not on the stack. When I do this open, it calls directly to here, so the GUI code is on the stack and the networking code is on the stack, but the loader is not. The URL loader is not. So that open would fail. Okay, any questions on that? Okay, some of the other protections in Java that you may already be aware of, since you do know some Java programming. You probably don't know this part, that a program can't modify the annotations on its own stack frame. Remember, the annotation is what's saying, yes, you know, this stack has permission. That was those permissions that we had for a particular stack frame to say, yes, it has permission to do a particular operation on a resource. So a program can't change its own annotations. It can only Java can only manipulate objects for which it has a reference, and it can't get a reference to its own stack or anything else in the protection system. Okay? Type safety is another thing enforced by the load time and the runtime, where Java programs can't access, say, a pointer as an integer or an object reference as an integer like you can in a language like C or C++. And Java also has encapsulation. Okay, so here Java has a number of things that help protect the resources in a system. Any questions on that? They're just more language protections that are available in a language like Java, in addition to what the operating system already does. Okay, your homework for the week, I want to just kind of go over it with you just so you have an idea of the kinds of things you should be thinking about when you're answering the question. The question says, describe how the Java protection model would be sacrificed if a Java program were allowed to directly alter the annotations of its stack frame. Remember, it's these annotations in the stack frame when it's looking up the stack to say, you know, does it have permission or not? What would happen if a program could change it? If the program didn't have, you know, access in the example we looked at, what if the program didn't have, if it could actually change that permission for sockets to say, yes, it can access sockets, that open could go through even though it wasn't supposed to. So that's really what you have to think about here. What is the purpose of annotating a stack frame? Why do we do that? Or why does the system do that? And what would the risk be if a program could change its own annotations on a stack frame? So that's really the questions that you want to answer in your homework assignment. Any questions on that? Is that clear what the question is asking? Okay, we just talked about how the annotation works, where it looks back through the stack because it annotates it to say yes, it has permission or not. Okay, the other question is, how can systems that implement the principle of least privilege still have protection failures that lead to security violations? Remember, with the principle of least privilege, we're limiting what a program or a user or a system can access to what it needs to complete a task. So think about that. Principle of least privilege limits what a program, user, or system can access based on what it needs to complete a task. How could a hacker still cause damage to a system? In other words, if I'm protecting it, if I have a program that has access to resource A, okay, it has permission and it needs it in order to do its job, so it's given permission to resource A. What if a hacker came in and modified that program so that it destroyed resource A, for example? It deleted it when it wasn't supposed to, okay? So you know, kind of think of that. Think of how a hacker could still damage a system even if it had this principle of least privilege implemented on the system. Okay, any questions on that? Okay, if you have questions, you know, if you're struggling with the homework, you know, you could always feel free to send me an email, and I can kind of help you think about it in a certain way. The other thing, I didn't realize we'd go this far over, but I decided at the end of this week to add a quick quiz. And this isn't a quiz that you're going to get graded on, but you may want to think about these questions. And I will send you these slides. What indicates the type of an object in a capability list? What does a control right allow a process to do? A lock and key mechanism is a compromise between what two access matrix implementations? What's meant by the term object when talking about protection, and what are the two general types of objects in a system? And what are the two disadvantages of using a global table to implement an access matrix? So what I'll do is I'll send you these slides, and after you've reviewed the recording or whatever, try to answer these. And then in another day or so, I'll send you the answers, and you can check it. It's just a way of kind of, thinking about some of the main concepts that we covered and see if you remember what these different terms mean. Okay, so that's all I have for now. If you have any questions, I'd be happy to answer them. Otherwise, have a good evening, and I'll be talking to you on the discussion boards, in email, or in our office hours or our class next week. Okay, so have a good weekend.